Let's take a look at another O of N algorithm. So another linear time algorithm. This one's fairly straightforward as well. Nothing we haven't programmed before. Public static int sum, which takes in a list of integers. Now here, I'm specifying that this is a list of integers. And also because I'm putting list here, it means that it can be an array list or a list. So put list over here. And now we'll just simply sum it up and return the total. Now I don't have to specify, basically, I don't have to put an E here or anything because, again, this is not, we know what type is going to be here. It is a list of integers. If I were to put this here, it actually if I were to put integer here, this communicates something completely different to Java. And it's saying, hey, integer isn't a class I'm looking for. Notice that the color changed. Integer isn't a class I'm looking for. It is a generic, and that is the symbol we are using for generic. So it is basically, it's a list of E, but instead of E, we're calling E integer, which is a weird name to give E, but there you are. So don't do it like that. That will give you a lot of weirdness. Here we're specifically saying it's a list of integers, so the method will only accept a list of integers. So for int I is equal to 0, I is less than, I think I will change this to array list to be super explicit about it. I is less than list.size. Let's go ahead and return total, which is a variable I haven't created yet. So we're going to do that up here. Int total is equal to 0. And what we do is that we simply say that total plus equals list.get I. No need to cast it because we already know that it's an integer. Store that total in total. Boom. So let's take a look at this. With total, so this is a for loop. We're taking in an integer list of size n. Okay, so there's n items in this list. And for each of these lists, we have to get that. What do we have to do? We have to get that item out of the list and add it. Adding is just a very simple statement. It's just two numbers added together, right? And computers are very good at doing adding. So that's nothing. As far as get, what does get do when it comes to array lists? We can look at there. Basically, it says, hey, check. This is the actual array list source code, which what it does is that it just simply gives us it just simply retrieves this index from, they call their thing element data. And rather, it looks like they keep a object. Yeah. It looks like they keep something that is actually a list of objects opposed to that weird casting we did. Also, they have transient, and I don't know what that means. So I'll have to look it up. But regardless, let's go ahead and go to my array list. Right? For my array list, what do? For our get method, we just simply do a simple check, and then we return a memory location using the array subnotation. And that is a constant time thing. It doesn't matter where in the index, what index you're at, where in the list you're at. Getting something from an array list takes constant time. Doesn't matter if it's the first item or the last item. How come? Well, if you didn't learn this previously, let's go ahead and go back to big examples. When you have an array, right, because an array list is built on top of an array, and we've got basically a bunch of items in it, right? So we'll maybe say that R is equal to 1, 2, 12, blah, blah, blah. Right, so on and so forth until we're done. Right, what gets stored in array is a memory location. Or what gets stored in R is a memory location like maybe let's go with something easy. 0x, that's just simply saying that this is a hexadecimal number, so the digits are base 16, which run from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A is 10, B for the 11th digit, and so on for until we get to F for the 15th digit. So maybe we're at memory location FA000000. Okay, so maybe we're like at that memory location. Okay, that's where array is. So the way that if we want to get say array of index like 7, what Java does is that it will go ahead and say, okay, I just need to do a simple computation. The address of what I'm looking for is at the array's address. So another array address, so that thing, plus the index times the size of element. In other words, how much each thing takes up, how much space each thing takes up in an array, which will usually be 32 bits because they're memory locations, I believe. So over here we've got, and so what this will do is that array address is just simply this one. This also happens to be the memory location of the very first element, index 0. So if we ask for index 0, we'll simply do return this. The address of the item we're returning is at this, plus 0 times whatever, because it doesn't matter if we're multiplying by 0. So we'll just simply return this. If we want index 1, it will be this plus 1 times another, however many bytes over we need to go, so 4 bytes. And so that will return memory location, say 0xFA00. Now let's go ahead and say array 1 will give us back FA0000, and that was 4 bytes over, so 04, because everything's addressable by bytes. So that will be the location of index 1. And then it will just simply increment by 4 each time. But this is just simply addition and multiplication, which is super simple for this to compute again. So again, it can just do this in constant time. It doesn't matter how big the list is, how many indices there possibly are. Multiplying big numbers, that's one of the things, if you ever learn about circuitry, it doesn't really matter how big those numbers are, so long as they're within the range for normal computation, we can just simply do that very easily. It's the same amount of time whether it's a big number or a small number. So, suffice to say, let's go ahead. So that was just a big aside. Let's go ahead and bring it back. This is constant time. This is a constant time operation here, but we are doing it n times. So this entire the entire thing is O of n, right? This is a loop that runs n times, where n is the size of the list. Each of those n things does a single constant time operation. Well, a couple constant time operations, right? We've got the, we go for the, we grab the, let's go ahead and think about it. We do the get call, which has to check the index, and then it returns the thing, and then we got to add it to here, right? And I just pointed at my screen and realized you couldn't see that, and now I feel like an idiot. So anyway, so that happens, but since they all take the same amount of time, no matter how big the size of the list is, this is a constant time. But the number of items we add will change based on how many items are in the list. So that's why it's O of n in total. Same thing for this one over here. Checking, we have O of n items to check. There's n items in the list. So doubling the amount of items will mean this takes twice as long. I don't think I need to run this for you to show that it will have the same effect, but I will go ahead and do so. And once that's done, I'm going to end the video. So if you've already got the idea, feel free to skip to the next video. So there. Right. Let's go ahead and do sum of a list integers for the listed sum is, oh, right. So we're going to print out the sum. Doesn't take long at all for it to compute that sum. Let's go ahead and bring it up to 100,000 over here, and then bring it up another multiple. So again, this adding doesn't really seem to take much time at all. So let's go ahead and add a more extensive slowdown in there. So 63 milliseconds. So maybe if I increase this by size 10, we should get... Nope, it's still very, very fast. 61. Really? Oh, right. I'm not slowing it down. My bad. So if I want to slow it down for each item, it needs to be in this for loop. So this should go monstrously slower. Yep. But it will end. So let's go ahead and go back to 1,000 items. Yep. I have slowed it down sufficiently enough. Those print statements are expensive, even though they literally do nothing. All right, so we've got 1,000, which took 546 milliseconds. So now if I double the amount of time it's going to take, this should double the input size. This should double the amount of time it takes. Went from 500 to 1,000 roughly. And so again, let's do this again at 1,000. And so multiply it by 10. We get 10 times as long.